Good morning, good afternoon, good evening, wherever you are in the world. Welcome to my show. My name is Diana Hooper, and I'm a postdoctoral researcher at the University of Helsinki, where I study cosmology, which means I study the universe, the contents of the universe, how everything evolves, how everything interacts. It's a great topic. I love talking about cosmology. I love studying cosmology. And I love coming here on Happs and chatting to everyone about all of the cool things happening inside the universe. Now, today is a special day. Today is Halloween. But as far as physicists are concerned, today is actually Dark Matter Day. So a few years ago, some physicists decided that there was going to be a yearly event for Dark Matter Day. So today is Dark Matter Day. So today we, of course, have to talk about dark matter. Now, dark matter is a very broad topic, and I'm not going to be able to cover everything by myself. So to help me talk about dark matter, I have 5 guests with me today. I think this might be my record for guests on Happs. So I'm just going to bring everybody here on screen with me. This should complete everyone on screen. Okay, welcome everyone. Thanks for being here, and hello to everybody joining in the comments. So nice to see you all, and thank you for the hi award, David. Okay, so let's just do a quick fire round of introductions, and I'm just going to go around clockwise. Elias, let's start with you.
Hi, I'm Elias. Yeah, thank you. So hi, I'm Elias. I'm a former colleague of Diana's in Aachen, Germany. I was, until very recently, a PhD student there in theoretical particle physics, more specifically in the part of particle physics that is quite close to experiment and focusing on dark matter. And now, for the last 3 weeks, I've been a postdoc at Fermilab in the US, close to Chicago. I'm actually joining from my temporary accommodation here from my hotel room in Naperville, close to Chicago.
Great, awesome to have you here, and obviously very nice to see you're doing well in Chicago. Sania, over to you.
Yeah, hi everyone. I'm Sanya. I was also a former colleague of Diana, also a former colleague of Ilias, because I was also in Aachen. Also a PhD student until very recently. I guess you can take whatever Ilias said and then just replace his name by mine, and it's the same story. So currently I'm a postdoctoral researcher at the McGill Space Institute for the last 1 month, I think. Yeah, and I also work on dark matter somewhere between particle physics and cosmology. So yeah, so dark matter theory and experiment, particle physics and cosmology, essentially.
Awesome. Felix, over to you.
Yes, hi everyone. My name is Felix. I'm junior professor at Aachen University, and in case you haven't made the connection, Elias and Sanya, until very recently, were my PhD students. And we've been doing a lot of exciting work about dark matter, how to look for it, whether we may have found it or where we're going to find it. And this is what I'm here for, to tell you a bit more about all that.
We are very happy to have your expertise with us today. Matteo, over to you.
Hello, everyone. My name is Matteo, and I'm a PhD student still. So I think I might be the youngest of the bunch, but I'm in Brussels right now, and I could pretend I work between cosmology and particle physics, but to be honest, I just do cosmology. So today I'll try to give you that perspective on the topics we're going to touch upon.
Awesome. And Sophia? Sorry, you were muted. Let's go again. I just unmuted you.
Thanks. So yeah, Matteo, you're not alone. I'm also a PhD student. So
good to know. So at least we had two.
Yes. It seems I'm the only one that's not from Germany though, or at least doesn't have some ties to Aachen. I'm at University of California in Irvine, and I do dark matter work as well. Also sort of cosmology, particle, I would say more on the cosmology side. And yeah, I'm really excited to talk about dark matter with everybody as well.
It's great to have you all here. I think combined we have enough expertise to solve the dark matter issues, so at least I hope we do. So that's the objective today. So we're going to pull out a new model of dark matter, solve all the problems. So as always, to everybody joining in the audience, welcome. Thank you for being here. Thank you for choosing to spend part of your Sunday with us. If you have any questions about dark matter or any questions about what we say, do feel free to ask them. I will guide the conversation along, but we will try to incorporate as many audience questions as possible. So please do feel free to jump in with as many questions as you want. We will do our best to try to answer them. Today, we will keep it on topic of dark matter, so any questions about other topics, we will leave for future discussions. So we've all talked a lot about, we've all mentioned the word dark matter now, but I guess we should get started with what is dark matter. So everything we see in the universe, everything we're accustomed to, everything from the stars in the night, you see in the night sky to us, we are normal matter. And normal matter only accounts for 5% of the energy budget of the observable universe. Then there's 25%, which is in the form of dark matter. So dark matter is this strange type of matter that can interact via the gravitational force, but it does not interact via the electromagnetic force. This means it does not emit light, it does not absorb light. As far as dark matter is concerned, as far as light is concerned, dark matter is kind of not there, which makes studying dark matter very difficult. And just to complete the picture, the remaining 70% of the energy budget of the universe is in the form of dark energy, which we know even less about than dark matter. But today we are going to focus on dark matter. So I want to start with a general question, and anyone can answer this, whoever in the panel wants to answer this question. So the first question is, what do we actually know about dark matter? Who wants to take that? Anything you think that this is something we know about dark matter?
Okay, I think I leave it for the experts. So don't count me in.
It's not such an easy question to answer, I think, because at the end of the day, we don't even know kind of if dark matter is in the form of tiny elementary particles or in the form of very extensive, massive objects like black holes. Right, so basically on that whole scale, we can imagine all kinds of different possible explanations for dark matter. A couple of things that they have in common is, I guess, by definition, that they all need to be dark, so they can't emit or absorb or reflect light in any way, or at least not in the same way as visible matter does. And it almost stops there, right? So you can say a few more things like that whatever constitutes dark matter must behave differently from visible matter, in the sense that we know how stars form by visible matter clumping together and then heating up and exploding and stuff. And dark matter doesn't seem to do that for all we know. Actually, even this, I think some people would argue against. But I think as a starting point, this is probably the only things that people can agree on.
Yeah, and to complicate things, I mean, it doesn't even have to be one single non-standard particle. It can be a whole new sector. So it can be the freedom. It's really what is killing every theory, because then if you open up the possibilities, there is really a variety of things that you could look at. So, but there are hints, like there are ways to at least exclude part of the possibilities. And in particular, personally, what I've been focusing on is something called the cosmic microwave background, which is some sort of primordial light that is coming towards us from very early in the universe. And we use it to understand how the universe expands in many different regards and possibilities. And you could constrain dark matter models in a way, let's say, any difference with respect to the standard model will impact the way this CMB spectrum looks like, so that if it deviates too much from what we see, this is a way to at least understand what dark matter is not.
Yeah, so I started with a loaded question of what do we know about dark matter, and I think we all agree that we're better at figuring out what dark matter isn't.
Yeah, exactly.
So it's very, or not easy, but we can come up with a new dark matter model and then test it and then reach a conclusion, okay, this is not the correct answer. So it's easier to figure out what dark matter can't do and what dark matter isn't than it is to actually figure out what dark matter is. And I see there's already a great question from Scott in the audience here of a notification that you saw a headline recently. As always, be careful with popular science headlines. They are somewhat clickbaity. But there was one recently, apparently, of scientists of a new theory without dark matter. So let me raise that question of, do we need dark matter? Why do we believe in dark matter? Who wants to take that?
I think, like, just jumping off from what Matteo said about the cosmic microwave background, I think that's kind of like our most precise probe of dark matter. So it's from the CMB that we essentially know how much dark matter there is. and it's impossible to explain the CMB without invoking some form of dark matter. Yeah, I guess that's all I would say.
Yeah, I mean, very broadly, kind of dark matter is about holding stuff together, right? This is basically where our understanding of dark matter comes from, that we need some kind of extra contribution to gravity, that the gravity of visible matter isn't enough to somehow form all the systems that we see. Like gravity, like galaxies, the way that we see them would just fly apart if there wasn't an extra force, kind of an extra thing binding stars together, and galaxies would all be flying apart, and gas wouldn't somehow clump if it wasn't for dark matter. So in a sense, this is kind of on an intuitive level, I think this is what we know about dark matter, right? It clumps stuff together.
Yeah, and I just want to say that this is actually the inspiration for the title today. I know my title is also slightly clickbaity today, but the support network of the universe, this title is because dark matter really is the glue that holds all of the structures of the universe together. So without dark matter, we wouldn't have galaxies, we wouldn't have clusters of galaxies. So dark matter is really the scaffolding on which other things can form within the universe. So
large-scale structure.
Large-scale
structure.
Yeah, exactly. So, Sophia, you've worked on large-scale structure. So do you want to explain how we relate the large-scale structure to dark matter? And I'm going to flash the image that we usually think of in terms of large-scale structure while you discuss it.
Yeah. So, I guess so. That's not particularly like what I've worked on, but like my work's a little bit different than that. But I mean, I guess everybody somehow kind of derives their work from this. But yeah, let's talk about this. So this is like the cosmic web, and this is from the Millennium simulation. What you're seeing here is basically like kind of like a network of dark matter, and you might kind of, I guess, liken this to neural networks. Oftentimes people will think of neural networks when they see this image. But what you see here is something that you can only form if you have dark matter. It comes like in the very early universe, before before photons decoupled from matter. So like before the cosmic microwave background. So like when everything was opaque, everything was bouncing off of everything else. You have matter is it interacts with gravity, and the universe isn't entirely uniform, and so matter tried to sort of fall into these little pockets where we're into regions that weren't entirely uniform, and try to sort of form these seeds, and photons would come and kick matter out and not let it sort of coalesce under gravity, because normal matter interacts with photons. But dark matter also interacts with gravity, and so it didn't have that problem, and it was able to coalesce into these pockets without being kicked out by photons. And so it continued to do that and form seeds while normal matter kept getting kicked out. So and so after continuously, this continued, and eventually when photons decoupled, and then we had essentially the dark matter seeds for where normal matter would essentially kind of fall under gravity towards. So you would say then that dark matter kind of formed the seeds for where galaxies would form today, and that's how large scale structure formed, and that's how you see all these little I guess sort of filaments and this network. It was formed because dark matter existed. Without the dark matter, you wouldn't have that.
So thanks for that explanation. Sorry, go ahead, Felix.
I think Paul is exactly right with what he wrote in the chat, right? So it's really kind of dark matter was there first, right? And then somehow galaxies happened after that. So really, it's much more appropriate to say that dark matter clumps have galaxies sitting in them than the other way around. And in fact, it's entirely conceivable that there are dark matter clumps with no galaxies in them. It's just that they are so hard to spot that we don't know.
But
yeah, we're still looking for those.
I have a question for Sophia, if I can, personally, because I mean, you've heard a lot of the overlap between the role of dark matter and that of gravity, and so essentially, it's even possible that there is no particle, but that just our understanding of how gravity works could be wrong, or at least it could only apply to the systems that we have observed so far. And there are certain aspects of our observations that you could explain with different theories of gravity and others that you could not. And my question is whether you think that large-scale structure formation could be explained by a modification of gravity without the assumption of dark matter, or if that is really a strong hint to the existence of dark matter.
No, I think we require dark matter for that, actually.
Okay.
Because without that, then you're not going to be able to have that, you're not going to be able to have regardless what you do in the early universe, normal matter and photons interact. We know this, right? And so you're going to have normal matter getting kicked out of pockets no matter what you do. Dark matter doesn't do that. So it doesn't matter what you do with gravity, right?
Okay.
And so regardless of that, you're going to need dark matter in order to be able to form the seeds for the dark matter for the galaxies that we see today. So you're going to need to do that in order to get the large scale structure that we see today, because you're going to need to have dark matter to be able to form that. It's otherwise, like, normal matter it's not that normal matter can't form structure. It can. It's just that it wouldn't form the structure that we see today. It's just not, there's not enough time for that to be able to do that. And so no, I don't think that, that without dark matter that you can just get the large scale structure. Okay. I mean, I would love to hear from, like, from the more advanced people in this group.
Yeah, I think you certainly can't explain it, right? So, I mean, you could pretend that basically the universe just happens to be in the state in which we find it, and then kind of as far as observations in the present universe are concerned, it's more ambiguous, right? There, I think what Matteo said is exactly what we have to kind of struggle with, that modified gravity and dark matter can somehow give similar or competing explanations for various observations. But then, of course, we like to understand where things come from, right? Ideally, we would like to be able to somehow trace back the present universe all the way to some kind of singularity, what we call the Big Bang. And conversely, to kind of starting from very simple initial conditions, explain or predict something that looks like our universe. And dark matter seems to be the best way of doing that.
Right, yeah.
Yeah, so I see we have a couple of very good questions in the comments here about dark matter interactions, but I actually want to save those for in a minute and stay on this topic right now with why we believe in dark matter, or why we believe that dark matter is currently the best explanation we have. So we've already covered things like the CMB. Of course, I flashed that image as soon as someone mentioned CMB. We've already covered large-scale structure. But now maybe we can go into some of the other, slightly more local, maybe, or local from a cosmology point of view, other ways that we know that dark matter might be out in the universe. And I want to discuss, or I want somebody to discuss, whoever wants to volunteer for this, the idea of rotational curves, because rotational curves was one of the first ways that we were actually led to believe that there could be something out there that we can't see. So we haven't heard much from Elias and Sania yet, but if one of you two like to take rotational curves, if not, feel free to say no and I throw it to somebody else.
I can start. I mean, maybe the people who are more astrophysics savvy than me can at some point take over. But so the basic idea is extremely simple. The basic idea is just that when you have stars rotating around the center of a galaxy, then to keep them in orbit, you need gravitation that pulls them inward. And the faster they're going, the stronger the force needs to be. So this means you can relate the total gravity that is exerted by the matter in, for example, a galaxy, to the velocity of the stars orbiting in it. When you just observe these velocities, for example, by looking at certain spectral lines by a spectral line of hydrogen, that we know has to lie at a certain frequency. From that, we can, through the redshift of it, we can infer how fast the stuff is going. What people have observed many decades ago, so in particular Vera Rubin is associated with this discovery, is that the stars are orbiting too fast in the outer parts of the galaxy relative to the gravity that is exerted by the visible mass. So in other words, if you just had the visible mass, then and the gravity that is exerted by it, then these stars couldn't be held in orbit at this velocity. They would just fly apart. So then you can turn this argument around and say, given that they are rotating at this velocity, or revolving, I guess, revolving around the center of the velocity, there must be more gravitational force pulling them inward, keeping them on that orbit. And specifically, to make it slightly, so to give slightly more detail, what we see is that what we just saw was a rotation curve. So this is the velocity with which stars are rotating as a function of the distance. So the velocity here is on the y-axis, and then on the horizontal axis you have the radius. So this is the distance from the center. And what you would expect, as you see, this is this line, this dashed line expected from the visible disk. What you would expect if you just had the visible stuff there is that the velocity falls off, so roughly as 1 over the square root of the distance, as a function of the distance in the outer parts of the galaxy. And what we instead see is that it sort of plateaus and goes to a constant, or even in this velocity, in this rotation curve, I guess, even goes up a little bit. And for that, we need some other stuff that explains that explains all of the gravity there, so to say, that pulls them inward.
As usual, I forgot to unmute myself, happens regularly. So yeah, we need some other source of gravity, because just what we can see is not enough to explain the rotation curves of objects. And as you very nicely mentioned, this was initially proposed by Vera Rubin and investigated by Vera Rubin many years ago. And it's considered one of the first real evidences for the existence of dark matter. But we've already seen quite a few: CMB, large-scale structure, overall structure of the universe, rotational curves. There's another one that I think a lot of us like. In fact, for a very long time, I believe my profile picture on Happs is still me in front of a poster of the bullet cluster. So Sunny, do you want to tell us about the bullet cluster and what it means for dark matter?
Yeah, sure. So are you going to bring up a picture so I can talk through it, or should I just start talking? Okay, great. So the bullet cluster is actually just like an image of two colliding galaxy clusters. So when you think about a galaxy cluster, you essentially have like a lot of stuff in it. So you have like stars and objects and etc. But most of the cluster is just composed of gas, and otherwise it's just empty space. So if you have like in the universe, you could have these situations where two clusters would actually collide with each other. And whenever this collision happens, most of the stars and most of the massive objects in those clusters would just pass through, just because most of it is made up out of empty space. But then all of the gas that's present in both of the clusters kind of interacts with each other and clumps in the center. And you can essentially, so most of the gas is what the visible part of the cluster is. Like that's just the gas. So depending on where the gas is, you can essentially estimate how massive these clusters are. And that is essentially like what this image of the bullet cluster is. So it's basically a picture of, okay, so there are two parts of it, right? So the first part is like, if you just focus on the pink regions, that's essentially the gas interacting of the two clusters, and that emits basically X-rays, and we can see these X-rays, so we know kind of where most of the mass of the cluster is. But what you can also do is figure out how light in sources that are behind the cluster bends when it passes through it. And so we know that any massive object in the universe essentially bends light. And so we can figure out how how massive something is by figuring out how it bends light, essentially. And so what we can do is we can create a mass profile of these clusters by just looking at the way it bends light that's coming from behind it. And that's what the blue regions in this picture tell you. So the blue region basically tell you that this is where most of the mass of this cluster is concentrated based off of these kind of lensing measurements. And then the kind of the hint for dark matter is that if the clusters were essentially made up of visible stuff, we would have like a complete overlap between these pink and blue regions. So most of the mass is in visible sector. Visible sector kind of gets tangled up in the middle, emits X-rays. And so essentially the two things should be completely overlapping. But what we actually see is kind of this disjointed image where you have a distinct kind of region where the visible mass is concentrated and a distinct region where most of the mass is concentrated, which is the blue region. And that tells us that kind of most of the mass in these clusters is not actually made of something that we can see. And that gives us a very nice hint for dark matter. And it's called the bullet cluster, but because it kind of looks like the shock wave that you would expect from like a bullet striking a target.
Doesn't matter how many times I hear people talk about the bullet cluster, I always love listening to that explanation.
Can I add one tiny comment?
Please, go ahead.
So I just want to add to Sanya's really nice explanation that the fact that we have seen dark matter, so that the fact that the bullet cluster implies that the dark matter distributions went through each other relatively unimpeded, also tells us that so it gives us an upper bound on how much dark matter can interact with itself. It tells us that dark matter particles can't have too strong interactions with each other. So that's actually another thing. Apart from just it being there, that's another thing we can learn from the bullet cluster.
That's an excellent comment. Sorry, go ahead, Matteo.
No, I'm just sorry. I just meant this. It also ties very well with the question by Scott.
Yeah, this is exactly where I wanted to head in a minute. I just wanted to wrap up this as like why we believe in dark matter.
I'm sorry.
So no, it's fine. I appreciate you keeping me on track as well because I can miss comments, so it's appreciated. So what we've discussed so far is different reasons why we believe in dark matter. We've seen things like rotational curves, bullet cluster, obviously the CMB up first, large scale structure. As we were saying before, sometimes you can say, what if we just modify gravity or change our understanding of the laws of physics? Sometimes you can explain rotational curves or you can explain some of these evidences individually. But when you take them all together, it's very difficult to find a model that can fit everything as convincingly as dark matter does. So I think that's how I would summarize why we believe in dark matter.
Before you go on to the next, can I just add one thing? So one thing that's curious is that we see dark matter basically everywhere where we look in the universe, like every galaxy we see, every galaxy cluster, cosmic microwave background, whatever. But it's surprisingly hard to somehow see dark matter in kind of the solar neighborhood or in the Milky Way. So this is something that I always find kind of curious, that it's actually easier to measure dark matter in a distant galaxy because you see it kind of from the side and you can measure how it rotates and so on. But the Milky Way, because we are inside it, we can't actually measure these rotation curves in such a clean way. And it turns out to be a much harder problem. And it's only kind of quite recently that I think there's consistent and significant data that shows that the Milky Way is exactly like all other galaxies. I mean, of course, we shouldn't expect the Milky Way to somehow be a special place in the universe, but just from kind of being rigorous, it's nice to see that we can, by kind of very carefully measuring motion of stars and so on, can make exactly the same conclusion that dark matter is basically everywhere around us, and this, of course, then also ties in to the chances that we have of detecting dark matter someday, right? So basically our understanding is that dark matter is everywhere around us, just like it's everywhere else in the universe.
Yeah, that's a great comment to add to that explanation. So thank you for that. So now I do want to go back. Please go ahead.
Sorry, this brought something up for that I feel a lot of people mention often, is that like and this was really a good point that you brought up, is like, measuring it in the solar neighborhood. So people often say, well, if we can measure it in galaxies, why can't we measure it in the solar system, right? But if you were to, when you sum up dark matter in a galaxy, there's so much more space in a galaxy than you think, right? Whereas if you look in the solar system, it's a very, very, very small region. So if you sum up the dark matter in like the solar system, I think if you look at the density of dark matter in our solar neighborhood, and you sum up the dark matter in the solar system, I think it's like 10 to the 15. I think it's like 10 to the 15 kilograms, which is a very, 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 very tiny amount. Compared to like the mass of the sun or whatever, so it becomes negligible, even compared to the mass of Jupiter. So, and this is why if you were to like, and don't quote me on that, it might be a little bit different. I think I just remember I calculated it once, a back of the hand calculation, but it's very small, something like this. And it's because the solar system is a very small little, like, it's a very small region. Whereas like in the galaxy, you have between stars, there's it's about 4 light years distance between between every star that you have. That's a lot of space between every star, and the galaxy is 100,000 light years in diameter, and so that's a lot of dark matter to sum up. If you sum up all the dark matter in that region, and of course the density changes throughout the whole thing. But that's, yeah, I just wanted to mention that, because I thought that, like, a lot of people say that we should be able to measure it here, but if you look at the dark matter inside the solar system, it's really negligible compared to like the sun, because of how small our solar system really is in the grand scheme of things.
Yeah, I do like that this conversation is allowing us all to go off in different directions. I was very much expecting that to happen, and I'm very glad that that is the case, because I think we all overlap at dark matter, but in different areas. So it's nice to see the different aspects we focus on. I do now want to go back to 2 questions that were asked by Scott and by David, both of them related, so I'm going to tie them together. And it's about how dark matter behaves with other particles and how it interacts via the different forces. So there was Scott's question: is the current model supposing that dark matter can be interacted with physically, like could you bump into it? And David's question of, does dark matter interact with gravity in the same way that normal matter does? So who wants to take these 2 questions?
I can go ahead and talk about dark matter interactions, just generally. So all of the evidences that we have currently points us to the fact that dark matter does interact gravitationally. So most of the observational evidence that we have is related to gravitational discrepancies that we see, and what we predict, like in the situation where we don't have any dark matter. Any non-gravitational interactions are kind of at this point an assumption. So all of essentially all particle models of dark matter assume that there has to be some coupling between the dark and the visible sectors, but we don't know how small this coupling can be. So we do know how big it can be, because if it's bigger than a certain amount, that means that we would be able to see, for example, photons hitting dark matter and figure out like there's something there. But we really don't know how small it could be. So essentially, it could be 0, it could be very small but non-zero, and that's something that we are in the process of figuring out through like various experiments and various dark matter searches. But I don't think you should be worried about like bumping into dark matter just because it interacts so weakly that I mean, in principle, like okay, so we live in like a dark matter halo. So in principle, we are being bombarded with dark matter particles all the time. And it's just that the interactions are so weak that it just passed through. So we don't have to be worried about, like dying out of a dark matter wound or something.
It would make you very special though.
So
yes, it would. It would place bounds on interactions. So it would also be good for physicists, I think.
Yeah.
So one natural unit for dark matter that I always remember is that I think the local density of dark matter, if it depends on how heavy it is, but if it is sort of in the ballpark of many explanations that we have for it, which is sort of similar-ish to the mass of a proton, maybe 10 times, 100 times, 1,000 times that, something like that, then I think the local density is about 1 particle per coffee mug, roughly. And it's passing through us at like hundreds of kilometers per second. And that makes for many, many dark matter particles actually going through us all the time, which is kind of cool to imagine that this thing is actually going on.
We could all be dark matter laboratories if it interacted strongly enough.
There was a paper, but I'm not sure if I should. Maybe this is for the discussion afterwards. I think this would derail it too much.
Well,
But
given that it is Halloween, I think we can go ahead. I already just mentioned the paper because I know what paper you mean. I just mentioned it in the chat, but it is Halloween, so we want. I'm just going to mention this paper briefly here. If you want to,
yeah, I mean, I can. Well, so so it's a long time since I read that paper, but it was basically about unexplained deaths from dark matter, right? So it was about the fact that certain candidates for dark matter could, in principle, if they interact with people with a strength above a certain size, they could, in principle, kill people. And then people summed up I think they were looking at dark matter models where the energy of a dark matter particle passing through you was sort of comparable to a bullet. And then they looked at statistics of unexplained deaths all over the world. And from the fact that there aren't more unexplained deaths than this number, derived an upper bound on the interaction of dark matter with ordinary matter, or in this case, people. Now, I should say that there are, how should I put this? There are considerable systematic uncertainties associated with this analysis.
But even in the optimistic version, is it even comparable with bounds we get from actual experiments?
No, I think it was orders of magnitude weaker. But the idea was you could rule out bullet-like dark matter, because if dark matter behaved like bullets, we would have unexplained bullet wounds.
Because in principle, you have many humans.
So I think they were looking at, I think they derived dark matter bounds in mass range for dark matter that is sort of outside of what we normally constrain with experiments, but I'm not sure. But yeah, it was probably orders of magnitude weaker, but I don't want to. I'm not entirely sure where the bounds fell.
Now, whoever said physicists don't have fun needs to read that paper. I remember when it came out, I loved the paper so much. It was so fun. Sophia, I think you wanted to talk about dark matter interactions a bit as well.
I mean, so I actually remember doing a back of the hand calculation. I don't think it had anything to do with that paper. It just had to do with the density of dark matter in the local neighborhood, and the really I guess maybe like consider a body being like a sphere or something, taking like the volume of a human and whatever, and it's about, and I think taking the dark matter to be the mass of the proton or something like that, about 20,000 or something like that, maybe 10,000 dark matter particles to be in your body at any given moment or something like this. So I don't know, maybe you can check my work or tell me if I'm completely off or if I'm somewhere.
About right.
Yeah. Okay, great. I'm glad to know. Okay. So there's something for everybody to know that, if that's true, if dark matter is the mass of a proton, then you have about 10,000 dark matter particles passing through you at this moment. And happily, you don't feel any of them because they will not hit you as bullets.
But we know that because there's a paper on that.
Yes. Go ahead.
No, you go ahead. It's okay, sorry.
No, the only thing I wanted to mention was that one of the things that we do study is the possibility that dark matter interacts in different ways than interacting with regular matter. So we because we've been studying dark matter that doesn't interact at all with other dark matter particles, we've been now looking at different models that perhaps where dark matter interacts in under different interactions than the standard model. So maybe there's a whole dark sector which would lead to dark forces and things like that. And so that's kind of like one of the types of dark matter that I study. And so that could lead to, for example, a whole sort of dark sector of dark matter, and like, the bullet cluster would also like give us limits on how much like a dark matter particle could interact even in that case too. So I just wanted to mention that as well, because that kind of like just opens the door to a kind of I guess a dark world, if you will.
But I
Right.
mean, to tie a bit, it's been underlying to me in the answers of you all, and to go back to the questions. I mean, in principle, as Sonia said, it's safe to assume if you like the option that dark matter is a particle, you assume that dark matter interacts gravitally with everything else like normal particles would, because it has a mass and gravity works just purely based on a mass. The problem is that in a model where dark matter only interacts gravitationally, everything is sort of boring. Because again, to go back to what Felix said, if you try to project the history of the universe back to its origin, and everything is just gravitation, then nothing really interesting happens. And for us, the fun is really to assume that there is something non-standard, like dark matter interacting with photons or electrons or whatever you might like, and try to figure out what these assumptions mean, or either on cosmological scales or on much smaller scales, like what would happen in an accelerator, for instance. So it's really a game we play because of how blind we are to the actual properties of dark matter. And then we try to play the game of what if, and based on the results, we try to find out whether there is something in that model or not. And that's the game. So in principle, it's fairly possible that the dark matter is very boring, but it's not a fun game to play. So we try to change the rules to make it more entertaining to us and more interesting.
Also,
That's a really
I'd
good
like to-
explanation. I love that.
Can I expand on that a little?
Go for it.
Go
Okay,
ahead.
so there's this aspect to it, but then of course you might say, like, there's no law of nature that tells us that the universe has to be fun or kind to physicists. But there is also another aspect to this, which is that in principle it is possible. So we have no incontrovertible evidence that dark matter has to interact in a different way than just gravitationally. But we have good reasons to think that it does, other than just that otherwise we can't say much about it, or we can't detect it in our experiments, or it's less fun for us. And this has mostly to do with how it seems likely that dark matter was produced in the early universe. So for the currently best explanations that we have for how we ended up with the dark matter abundance that we have, with this one number that we've really measured, how much dark matter there is, for these best explanations to work, there needs to be some interaction with dark matter, bit of dark matter with ordinary matter, to produce dark matter in the early universe.
Also, I
Now,
would just
it could also be, it is also possible that we can end up with a bright dark matter abundance without those interactions. But we have compelling reasons to believe that dark matter has also other interactions. But of course, at this point, this is an assumption that we are currently constantly testing experimentally and through cosmology as well.
Yeah. Also,
Celia,
just
you wanted to add something?
Yes, I just wanted to add, like, so of course, as everyone keeps saying, that we don't really know whether it interacts non-gravitationally. But I think another reason to think that it does is if you accept the fact that dark matter is a particle, then using our framework for the mathematics of how these particle interactions work, and like looking at the symmetries that we know nature satisfies, you inadvertently would have, like, depending on the kind of particle you want your dark matter to be, you would inadvertently have some interactions in this mathematical framework that we have. So you can always write down an interaction. And then the trick is to figure out what the value of this interaction is. And to say that the value of this interaction between the dark and the visible sectors is 0 means that you're claiming that an additional symmetry exists beyond what we know. So that's kind of one other way to look at it. So if you just say the dark matter is a particle, so for example, if you say the dark matter is something like a photon, not exactly a photon, but like a dark photon, then you can always write down some interaction between this photon and the photon that we know and love. So that's always like a possibility.
So I see that my comment on the dark matter being no interactive touch on some soft chords, but yeah. So ideally, yes, the dark matter would need to interact. It's just that to try and rephrase more accurately what I meant to say is that on cosmological scales, the only interaction that you really need is gravitation. But in order to, and again, I think Felix mentioned it, you want your model to boil down to something that we can describe mathematically, something with a foundation that fits in everything else. And in order to do that, as Ilya and Sania said, you need, first of all, to produce the dark matter, then you need to describe it in terms of what we know. So there is a big open door to interactions. It's just that it's not straightforward to understand whether they are there or with what.
Yeah,
So
I would.
Go ahead, Felix.
I would agree with that sentiment. I think we, as Elias and Sanya explained, there are a lot of good reasons why we can be optimistic, but then of course you can also be pessimistic, right? And the pessimistic approach would be to say there's no way we're ever going to see dark matter particles in the laboratory because they don't give us any way how we can probe them. But then how do we make progress, right? What do we learn? And the way the scientific method works is you make a hypothesis, you see what that hypothesis predicts, and then you try and figure out ways to test those predictions, right? And this is kind of the only way that we know how to make progress. So it's clear that we start from hypotheses that give us something to do. I would say it's a bit more than a game. It's kind of how we do science, right? We predict something, we see if we can measure it, and then we start again. There's this comparison that's often made. You will all know this, but I'll say it again, which is that searching for dark matter is a bit like searching for the keys that you've lost on your way home, just under the lamppost, because that's the only place where there's light and you have a chance of finding the keys, even though you could have lost the keys anywhere on the way from the pub to your place. But you just, you're not going to find them if they are somewhere where there's no light. And this is a bit how we search for dark matter, right? We try and test the models that make testable predictions, basically.
I always love that comparison. So thank you for bringing that up. I do like how we took one question on interactions and turned it into a full discussion. I love all the directions we've given it. And I very, very briefly want to answer Joel's question here before we move on to another question that I want to throw at everyone. So we have a comment here from Joel of what if dark matter doesn't interact with gravity? And basically the only thing we know for sure about dark matter is that it interacts with gravity. So if it doesn't interact with gravity, I would argue that it's not dark matter, because all of the evidence we have for dark matter is in the form of the gravitational force. So now I actually want to move on to a question that I want to ask all of you. And we all here work on dark matter, but we work on dark matter from very different aspects and different directions. Just want to shout out David Dunn here in the comments. If anybody doesn't follow David Dunn, he's an astronomy professor here on Happs. Be sure to follow David as well for more astronomy and space stuff. So we all work on the dark matter problem from very different aspects. So I'd like us to all go around and just say which approach we all take to the dark matter problem. So I'm going to kickstart it off, and then we'll go around with everyone else here. So I've usually tackled dark matter from a cosmological perspective. So rather than looking at these underlying possibilities of what is dark matter allowed to do in terms of particle physics and symmetries and underlying motivations, my approach has been to take cosmological observables like the CMB or the overall distribution of galaxies in the universe and ask the question of, given these cosmological observables, what would dark matter be allowed to do? And this is something that we've all touched upon a bit in the discussion already. One thing that I specifically worked on was interaction. So asking the question of, given the CMB that we've seen, how much could dark matter interact with photons, for example, or with baryons, or with another component of dark matter that doesn't have mass. So my approach is always taking these cosmological observables and then trying to basically tell dark matter what it is and isn't allowed to do. So that means that I often remain blind to the underlying particle physics. So I don't ask, like, is this physically motivated? Just, would the universe allow this? So it's more of a top-down approach, but we will hear very different perspectives to this. So Felix, I'm going to start with you because I know you do have time constraints. So do you want to tell us how you work on dark matter?
Yes, where to start? I think I'll start with something that I kind of got fascinated by recently, which is that we can somehow try and look for interactions of dark matter particles by making extremely precise measurements of things that we understand extremely well, meaning that we somehow build a laboratory in which we can measure, for example, a single atom or a slightly more complicated particle about which we know how it interacts, how it decays, how it scatters, and these kinds of things. And then we try and measure all of those properties as precisely as we can, and we compare that to the predictions that we have from our understanding of particle physics. So in principle, we should be able to make perfect predictions. We have what is called the standard model of particle physics, which we believe describes all known particles and interactions in what we call visible matter. So we should be able to work out for every particle how it behaves. And now the name of the game is to see if you can see any deviations between those predictions and measurements. And this could be a response to magnetic fields. This could be measuring how long a particle lives before it decays into some other combination of particles, or into which particles it decays, or in what direction those particles are emitted, all these kinds of things. And as soon as you see deviations between the predictions and the observations, then you need to understand where those come from. And they could come from a dark matter particle, which just happened to be passing by and scattered, or somehow transferred energy to what you're measuring, or even to be more crazy, what we call virtual effects. So particles which are kind of just quantum fluctuations. They exist for a short amount of time, just to change your measurement and then disappear again. And all of these things we can probe with super precise measurements.
Awesome. It's just so fun to think of all the different things we can try to do to learn about dark matter. So I'm going to alternate more cosmology, more particle physics. So Sophia, I'm going to throw the question to you. How do you go about approaching the dark matter problem?
Okay, so so for me, I guess I'm kind of like very much on the interface of like so so somebody mentioned like my handle. It's really astroparticle because it's astroparticle physics. So yeah. So it's astroparticle. It's just a mashup of astroparticle and girl. It was just a thing that I came up with because I do astroparticle physics. And what I do is basically like I essentially kind of I kind of look at I look at what I look at observations, and when I see things that look strange in the universe, I go and look at models, and then I'm like, okay, well, let's see what's wrong with this model, and if I can tweak this model and make it kind of, I guess, fit what I see in the universe better. And so so I guess to make it clearer, I don't do observation, but I try to make say dark matter fit better, because it sounds a little bit strange, because the kind of dark matter that we've been working on doesn't work, or at least okay, that's an overstatement. It does, but it kind of seems to fail in certain areas. Like when we do simulations on small scale galaxies, we find that it doesn't get them right. And so like dwarf galaxies with the standard dark matter paradigm, which is a type of dark matter that doesn't interact with other dark matter particles. So like cold collisionless dark matter. So that's dark matter that doesn't see other dark matter particles at all. It creates small dwarf scale galaxies or dwarf scale dark matter halos that are too dense in the center. And so like if I turn on self interactions, that fits observations better. And so that's kind of what I do is I kind of test these models, and then maybe I'll, you know, add a tweak to it, or kind of like, you know, tune something, or add some sort of, I guess, I might like throw in something new and see how it works, or to try to, I guess, maybe explain observations better. And what I'm doing now is taking, like, that's just generally how I try to probe dark matter. But what I'm doing now, which I think is really cool, is I'm trying to explain supermassive black holes. And so using dark matter self-interactions, because it kind of leads to a consequence of this thing called gravital thermal collapse, where you can actually get a black hole in the center, because the way that self-interactions kind of result in this sort of gravital thermal catastrophe, which can result in the collapse of a dark matter halo. It can produce seeds in the early universe, which could result, which could be like seeds for supermassive black holes, because we don't know how these supermassive black holes were formed. We know how like regular stellar mass black holes were formed, and so essentially, I guess that's kind of how I approach dark matter. And then what the work that I do now is that. Yeah, so I hope that makes sense.
Yeah, and let me just add that if people want to know more about that, I did a whole Happs with Sophia some weeks ago, I think, some months ago by now, where we went really into detail on all of these topics. So do go check that out. In fact, I think everybody here on screen has joined me before except Felix. So it is your first time here, Felix. Thank you for joining again. Elias, let's go on to you because we're alternating. So Elias, do you want to tell us your approach to dark matter?
Well, I mean, I just finished my PhD, so I'm not. It's not like I already have a extremely clear niche. So I don't want to commit too much to one approach to dark matter. What I've been working on so far mostly is how we can test certain dark matter models at experiments, and in particular at collider experiments and other accelerator experiments. So the kinds of experiments where we could in principle, create dark matter here on Earth, for example, by colliding very energetic protons, as we do at the LHC, at the Large Hadron Collider. And then you get all of this through these collisions, get lots of energy in one place, and create loads of particles, most of which are described, almost all of which is described by the interactions that we already know. But depending on what dark matter is exactly, certain models of dark matter predict that in such collisions you would also make dark matter particles or other particles that are associated with dark matter that are part of the same model. And by looking at what we see in the detectors in these experiments, we can infer things about dark matter and possibly even discover it. So I've worked so far mostly on the. So I should also say I'm not an experimentalist. Maybe this wasn't clear from what I just said. So I work on the sort of like a sort of theory support for experimentalists, which is a field that is called phenomenology. So the part of theory that is quite close to experiment.
Phenomenology,
so I would say
is
I'm
one of those words
principally
that we can't say.
Sorry?
Like phenomenology, every time I try to say it, I feel like there's just too many syllables there and it keeps going phenomena. Anyway, sorry, carry on.
I would say I'm like principally interested in what new physics there is beyond the physics we know. And that I think that dark matter is at the moment our best gateway to that, our best shot at finding out. So that's why
Nice.
that's sort of the main reason why I'm interested in dark matter.
Okay, so if we keep alternating, Matteo, it's your turn, and you can't just say what I said.
Yeah, exactly. I was going to say I have a extremely large overlap with Diana, but for sake of answering the question, so you can imagine that in trying to approach the dark matter problem, we have been talking about scales a lot, like solar system, galaxy, large-scale structures, cosmic microwave background. But if you think the scale is more a way of talking about energies, because if you think about it, the energies of your dark matter or the amount of interactions they can have really depends on how much matter there is at that scale. So if you imagine the universe is very large, interactions are going to be very low. And if the universe is very compact, every particle is going to interact a lot. So if you want to learn about dark matter interacting, you either look at the large scale effects of dark matter, or you go back to the very, very, very early universe where the dark matter was interacting a lot, and therefore its effect on the way the universe expanded were enhanced. And in this way, also in a sort of an untold way, there is a threshold before which the interactions are so much that you come more from a particle physics perspective. And then there is a threshold or like a moment in the universe where the large scale impacts become more dominant, and therefore you start to talk more about cosmology in a way. This is not, don't take my word for it, but it's more like an unwavy way to explain the difference between the two. And before we talked about the way dark matter can form and how that impacts the rest of the evolution of the universe. And this crosses a bit this border between the particle physics approach and the cosmological approach. And this is why at the beginning, everyone said we are both working at the bridge between the two fields, really, because I think everyone is very much involved in these particular dynamics. And this is sort of something I've been looking at as well, trying to understand how dark matter can form and how this translates into possible effects on the cosmic microwave background, on today's structures, and so on. So it's really, again, this talking between particle physics and cosmology, and between small scales and large scale effects.
Awesome. I do like that a lot of us are highlighting this overlap between the different fields, and this is something that I will come back to later as well. But Sania, it's your turn.
Yes. So I think, right. So I think, like Ilya said, like I just finished my PhD, right? So I don't want to commit too much. But I think like my perspective on dark matter is essentially similar to what Sophia said, but kind of flipped around. So Sophia mentioned that she looks at cosmological observations and tries to figure out how different particle models can you can make that work better. I come at it from a more particle perspective. So I look at essentially what kind of models, like identify interesting models. So that's one thing. So the thing with building a particle physics model is that you can just you can essentially, since we know so little about dark matter, you can essentially build a highly complicated model that basically will solve all the problems just by virtue of the fact that we don't know anything, right? So you can just add in more parameters, keep tuning it, and then you have an answer for everything. So I think, but my perspective is mostly to do with how you can simplify this process. So essentially you boil everything down to as few parameters as possible. And then you figure out kind of the phenomenology associated with this sort of model on different scales. So something that I've been looking at for the last couple of years is essentially how particle interactions get modified in medium. So most of, and this is related to something that we also talked about earlier, which is one of the main things about dark matter is we want to explain how it was produced in the early universe. So we want to explain different kinds of production mechanisms. And most of our theory kind of works on the assumption that all of the particle physics that we do in the early universe happens in vacuum. So that's how we do most of our calculations. But of course, like this isn't an accurate assumption, because we know that the early universe was kind of like a particle soup and everything was talking to each other and there was like a plasma. So what I do is kind of figure out how possible interactions between the dark and the visible sectors would get modified in the plasma and what that would mean for various dark matter production mechanisms. And then I try to figure out how, as the universe evolved, kind of dark matter would evolve itself. And then finally, then you come down to present day and figure out, okay, now we have this kind of ambient density of dark matter, and then we figure out how we can search for it at various kinds of experiments. So yeah, so it's a bit of everything, I guess. I like to think of it as like basically tracing the story of dark matter in different contexts, and of course motivated by certain like foundational assumptions, like things that we know really well, right? So like you can motivate your starting interaction by the CMB, for instance, and say we know the CMB very well, so we can't have too strong interactions. So we build a model that does not have these interactions. Yeah, so I guess that's that's my perspective on dark matter for the moment.
Nice, thank you. And let me just say again to both you and Elias, congratulations on passing your PhD recently, because it is no small feat. It is a big achievement. So congratulations again for that to both of you. And yeah, I think we've covered many different ways of approaching the dark matter problem. And I think this is such an important point that we really need to come at the issue from multiple angles. So we have been online for over an hour already, and I think if we don't cut this conversation off at some point, we're all going to be here talking about dark matter for 3 hours, because there's so many directions I want to take this conversation, and I'm sure all of you have many directions you want to take it. So I am going to instead skip a couple of my questions and ask a closing question to everybody. Depending where we want to be, if we want to be optimistic, pessimistic, let's see how we all approach this. So my closing question is, do you think we will find direct or clear evidence of dark matter within the next 10 years? Felix, let's start with you again.
It's interesting. So I don't want to start with a kind of cautious answer, but I guess I've been around for 10 years, so I've been asked that question 10 years ago, and of course, then at that point I was super optimistic, but then it hasn't fully played out in the past 10 years. But I guess the way I would answer the question is to say that what we really need to make sure is to recognize the dark matter signal when we see it. I think we are absolutely living in the age of data for dark matter searches, in the sense that we have spectacular experiments that can do all kinds of exciting measurements that should be sensitive to dark matter. But then the challenge is somehow, if a signal pops up in one of these experiments, how to be sure. And we have examples for kind of signals that have been around for a long time that could be dark matter, or could also be something else. And it's kind of very difficult to be sure, right? So I think my answer would be that I am optimistic that there will be things that look like dark matter signals in the next 10 years. But I think the real challenge will be to somehow be sure, right? To really convince ourselves that this is dark matter and not something else. And this I'm maybe a bit less optimistic about.
I do like that answer. And if I can ask you a completely off-topic question, someone in the comments who met you once has asked if you're wearing Halloween socks today.
No, I'm afraid not. Sorry. I don't actually own Halloween socks. Next year I will. Ask me again then.
Yeah, I'll have you on again next year for Dark Matter Day, and we expect Halloween socks next year. Okay, I'm just going to go around kind of clockwise from where we started. So, Matteo, do you think we'll find dark matter in the next 10 years?
Well, I mean, as Felix, I'm very optimistic that let's say the aspect that makes me so optimistic is that we are finding lots of mistakes, at least cosmologically, in the model that we believed 10 years ago was perfect. So we are really the data that we have is really reaching a point where we are starting to dig into the problems. And this is where the solution starts to come up. Because when you have the thing is that we are looking for problems. And for a long time, they were very difficult to find. And when they were there, they were always controversial. So to me, the key evolution has been finding those problems. Going in that direction will be the goal of the next 10 years. And my hope is that in the next 10 years, we will have at least a clear idea of what the problems are. They will be well defined in their features, and possibly the features that some particle will need in order to solve them. So maybe even, as Felix said, even if we are not going to know for a fact what the dark matter particle is, what the let's say the full spectrum of interactions is, at least we will know what it needs to have in order to solve those problems that hopefully will be well defined by then. So this is my hope, and in that regard, I am very optimistic.
Awesome. So before we continue, Felix, I believe you have to go, so let me just pass the floor back to you.
Yes, just to say goodbye. It's been great fun, not just reuniting with the various former members of my group, but to have so many chat messages and comments and everything. So enjoy the rest of Dark Matter Day. Happy Halloween, everyone, and see you around.
Yeah, thanks a lot for joining. It's been great to have you here, Felix.
Bye-bye.
Okay, so continuing around on how we find dark matter, and I do want to say Felix had to leave 20 minutes ago and stay because we were having fun with dark matter, so we do appreciate that. Sophia, I think it was, oh, everyone's moved around now. Sophia, I think it was your turn.
Yeah, so going off of like what Matteo said, I would say I'm optimistic as well. We know a lot more about it now. I think we're looking at it from different aspects than we were before. I feel like in the past we were very stuck on the WIB dark matter sort of perspective, and that's kind of like what we were looking for, is, you know, this sort of supersymmetric particle. It was like that was the one that it had to be. And so now that we've kind of, I think, opened our, or let's say I would say expanded our vision and sort of started to look beyond that that sort of model, I would say, I think we're looking more in the right, I can't say we're looking more in the right place, but we're looking more, I would say, we're expanding our parameter spaces in the way that hopefully will give us a better look into where we should be looking at. And I think 10 years is a good amount of time. That being said, we've known about dark matter for a very long time. But I feel like dark matter has made a lot of, like, at least model in terms of model building and things like that. It's made leaps of progress in the recent times. And so I think if we don't discover it in the next 10 years, we will be very much ahead. And yeah, so I'm optimistic in terms of like where we'll be 10 years from now, and hopefully we discover it.
Nice. I do like your answers. I'm going to skip myself and come back to my answer. Elias, it's your turn. Do you think we'll find dark matter in the next 10 years?
I mean, I don't know. I'm optimistic, but I mean, who knows? Especially given in a certain time frame, like in a specific time frame, like 10 years. I would also agree that there are new search avenues that we are exploring that that haven't gotten as much, that didn't get as much attention before, because we had more. We used to have somewhat more fixed ideas of what dark matter should probably be. We are also pushing the envelope of the experiments. Apart from looking at new types of experiments, we're also pushing the envelope of the experimental strategies that are well established. So, for instance, maybe I should mention this towards the very end now. There's a more professional version of the type of dark matter detection that we talked about at the very beginning with death by dark matter, where we talked about this paper that constrained dark matter interactions with ordinary matter by looking at unexplained deaths. That was sort of a bit of a, I mean, sort of a semi-joke paper. But there's a much more professional version of essentially the same idea, which is called direct detection, where we look for dark matter passing through large tanks of, say, liquid noble gas, or also nowadays semiconductors and all sorts of stuff. And we are pushing those experiments to the standard experiments to the limit where the strategies kind of stop working, where we're hitting something that's called the neutrino floor. So we're doing that very soon and sort of exploring that as much as we can. We are also expanding that strategy to smaller masses than we have looked at before, actually orders of magnitude smaller masses than we've looked before. But as always, I mean, it takes, with any of these experiments, it also just takes time to collect data. There are also axion experiments, like if dark matter is axions, which is another type of particle that we haven't mentioned before. There are certain experimental strategies that when you just tune your experiment to the right frequency, you can discover dark matter extremely quickly. So we might get lucky in the next couple of years with an axion experiment. But overall, I would say, I mean, we're in this for the, it would be extremely nice if we would discover dark matter in the next couple of years, but overall, even if we don't discover it in the next 10 years, we're learning more and more about it. And overall, we're in this for the long run.
I mean, in terms of our own personal academic careers, it would be amazing if we found dark matter, right? Because that gives us,
sure, but I mean, like in the grand scheme of things, we don't matter.
Sure. Celia, on to you. Are you an optimist?
I don't think I am like an optimist by nature, but yeah, I think it's kind of like easy to to bet against dark matter. So if I had to make a bet, I would probably bet that we wouldn't find anything, just because if you look at the scales, if you look at the range of parameter space that is actually viable, and we're only just, and it's not even just one dimensional, right? So it's not just mass, it's also couplings. And so if you look at like the experiments that we're running, we're looking at like a ton of different avenues, which is great. But if dark matter is just one thing, then it could be that it's just like this one point in the parameter space, and then we're just unlucky and we don't hit it. So so I don't know if we will find dark matter in 10 years, but I think what I do know is that because of all of the experiments that we're running and all of the theory calculations that we are doing, we would have a better understanding of what it isn't. And maybe that's how we end up discovering dark matter, is just we exclude everything else, which would be the long way to go about it. Or, you know, like Ilya said, we could just get lucky with an axion experiment and just see a signal. But like just looking at the scope of possibilities, I think I wouldn't make the statement that yes, we will definitely see dark matter in 10 years.
We might also look for dark matter and find something else.
Yeah, it could be black cats, like someone said in the chat.
Yeah, I mean, the goal in the end is to find out how nature works. It's not proving us right.
I agree. Yeah. I agree. So I see my, go ahead, Sophia.
No, please go ahead.
Yeah, I was going to give my answer to that question. So if you want to comment on what was just being discussed.
I was okay. Well, yeah. If that's the case, I was just gonna say, like, it, you know, I think like the worst case scenario is like if it doesn't couple with the standard model at all, then then I think like we're kind of you know that's a troublesome situation. In that case, then you know all we have is like gravity, which we've been looking at this whole time, and it's like, well, then here we go. I mean, like, I've been touching dark matter all this time, and that's all I can do. Right?
Yeah, no, I get it. So I think I am actually optimistic, because we're at a stage where we have people working on dark matter from many, many different aspects. We've seen today 6 different approaches with some overlap, in some places substantial overlap, but different approaches to the dark matter problem. And there are hundreds, if not thousands, of physicists working on dark matter. And I do think that we're coming up with new ideas. I mean, we joked about this idea of dark matter killing people, but it's an idea, it's something new, it's something different. And there are increasingly more and more ideas. Felix touched up on this as well, like measuring atoms to try to constrain dark matter. This possibility of seeing if dark matter can produce gravitational waves. Just like we're coming up with so many ideas and so many new ways. I'm sure most of them are going to be wrong, but some might not be. So I think there's enough people, enough talents, that this is a possibility. And I just want to emphasize and go on Joel's comment here. Is it going to be a sudden breakthrough or a gradual understanding over time? I think it's going to be a gradual understanding over time. And I do want to emphasize that science is not done by one person. It's not going to be one lone genius who's going to find dark matter. It's going to be a collaborative effort. This is why I think having panels like today is so much fun. And I think we all enjoyed it, at least I did, because it really reminds us that there are many ways to tackle the dark matter problem, and we're going to need input from everyone if we want to find dark matter. But I'm optimistic. I think within the next 10 years, we're going to open a stream one day of we did it, we found dark matter. And rest assured that the day we find dark matter, you'll be the first to know here on Happs, because I can guarantee that I will be jumping for joy here on Happs when that happens. Okay, Elias, we have a follow-up to one of your comments here. If you find something because you said we might find something that's not dark matter. So Paul is asking, if you find something in the right place in parameter space, would it by definition be dark matter?
Depends what you mean by the parameter space and what parameters you include. So if you just find something at one experiment that, so say for instance, we have a collider experiment or some other accelerator experiment. And we find a new particle there that has properties that, as far as we can tell from this experiment, matches the properties that we expect from dark matter. Then going on that alone, we can't be sure that it is dark matter. Because, I mean, dark matter is the stuff that makes up 85% of the matter in the universe. But it doesn't, like, no new particle that we find at a collider experiment, for instance, has to be necessarily the stuff. It might be, for instance, that it is in fact unstable and just looks stable to us at a collider experiment. Then if you discover it somewhere else, if you discover it in, say, a direct detection experiment, so with these experiments where we look for dark matter passing through a target and hitting one of the target nuclei, for instance, then we have a better hint that it might really be dark matter because it actually came from space and passed through this detector. But generally speaking, you need a combination of different experiments and different approaches to be sure that anything you discovered really is this stuff out there and not some other new particle. And of course, we would be very happy about the discovery of any new particle as well, also if it isn't dark matter.
Yeah, I think that is an important point, that if one group announces that they found dark matter, there's going to be a rush of other groups trying to find the same, because if only one experiment finds it, you kind of need reproducibility.
And that has happened in the past.
I do want to wrap up, but before I do, I just want to leave it open because I've kind of guided the discussion. So keeping it brief, is there anything else you want to mention before we wrap up?
I wanted to mention something. So like a lot of us, I guess a lot of the experiments that people know about now are like, ones that are still, looking for WIMPs or looking for axions and stuff. But I did want to mention, because I did mention that, there are models that are looking for dark matter that interacts with dark forces. There is an experiment at the LHC called Phaser that's looking for a dark photon, and it's called Phaser. So I'll just put it in the, I'll put it in the chat here, what it's called. It's called Phaser. If anybody wants to look it up, it was actually created by people at my school, Professor Jonathan Fang and David Casper. It's looking for a dark photon, and so and it also looks for neutrinos as well. But yes, I know. So this is we're really at a different we're at a different level in the dark matter search, and so this is why I think if any of us are really optimistic, it's because we're taking different steps now, and we're doing different things, and it's we're going to see different things, and so yeah. Stay tuned, because there are a lot of things to come.
So yeah,
I wanted to mention that because I think people don't know about this. Go
Yeah,
ahead.
the phaser is a relatively new experiment that belongs to a class of new experiments that are together often referred to as the intensity frontier. And these are, as you mentioned, these kinds of experiments that look for lighter new physics than, for instance, the Large Hadron Collider. And what's cool about phaser is that it is this type of experiment, but directly at the Large Hadron Collider. And there are also others at different accelerators. So if you want to Google this, the type of, like, this sort of stuff you have to Google is fixed target experiment or beam dump. They look for similar physics as phaser.
Nice, nice. I do like those detectors. Okay, any final comments? Anything else you want us to know? Sania, Matteo, anything you want to add?
I can just add a very quick comment. So we've been discussing like different kinds of dark matter particles, like dark photons, for instance, which is crazy. They can also be dark Higgses, and it could also be the dark matter is just like some kind of primordial black hole. And I think one of the possibilities that we should also keep in mind is that it could be that dark matter is all of these things. So it's not. It is just very complicated. So you also have axions, you also have black holes, you also have like dark photons and all together, but all of them comprising like some fraction of dark matter, which is why we kind of need these multi-pronged approaches to looking for it and thinking about it, because it could be that we do find an axion, but it turns out to be in part of a parameter space where you can't explain all of dark matter. So it's just a fraction. And given kind of, sorry.
Oh, no, sorry, I didn't mean to interrupt you. I just have a comment when you're done.
Okay, so I was just going to say that given the diversity that we see in the standard models, so we have like electrons, protons, and we have like all kinds of things in the standard models, right? So given that diversity, I think it's very safe to make the assumption that the dark sector itself is very diverse, not only in terms of the kinds of particles that we have, but also in terms of the kind of structures that can comprise dark matter. Yeah, go ahead, Elias.
I just wanted to say, yeah, it's perfectly possible that different types of dark matter candidates each make up a relevant fraction of dark matter. But that would be, I mean, the obvious counter argument is that this would be kind of a strange fine-tuning accident. So you might have different candidates for dark matter that exist, but what you would sort of naively expect is that maybe one is an order 1 fraction of dark matter, for almost all of dark matter, and then another one is maybe like, I don't know, 10 to the minus 3 of dark matter, 10 to the minus 5, 10 to the minus 10 or whatever. It's perfectly possible that like one is half of dark matter and the other one is half of dark matter. But that kind of leaves, that kind of, it raises the question. Let's just say that it raises the question why it ended up in this way.
Okay, I think we should talk about this offline, because I don't really see how it could be fine-tuning, and I don't want to derail this discussion. So
let's shelve that, because else we're going to be here all evening or all day for you in the US. We are reaching 1.5 hours. So, Matteo, is there anything else about dark matter you want to say before we close?
In a few words, like, even if we don't find dark matter, to me, there is still reason for optimism, because in looking for dark matter, already in the last decade, we've learned a lot. Even without the dark matter, already the excuse of having something to look for has brought so much information and new ways of looking at physics that, to me, it's still fascinating, regardless of what will happen. I'm very optimistic. So that's it.
Awesome. Thank you for that comment. So I think this has been great fun. At least I've really enjoyed myself. So I want to say a big thank you to everybody who joined me here on screen. I know you all took a chunk out of your Sunday to come here and talk about dark matter. And I know you're all very busy these days. So thank you to all of you for joining. This has been great fun. It's been great to have you all back on screen with me. I know you've all joined before. And I do plan on getting you all back on Happs again in the future. So big thank you to everyone for joining me here. And of course, a big thank you to everyone in the comments. We've had some really fun questions. You gave us a question about interacting dark matter, which led to lots of fun discussion among ourselves. So thank you for those excellent questions. And as always, thank you for tuning in. If you want to catch my next streams, be sure to click the subscribe button. I should be online again next Sunday, same time as today. Do be aware if you're in the US or in Canada that we've already changed our clocks. I believe you change them next week. So when I say I'll be online at the same time, that's the same time for me. Just check the schedule to make sure you're in the right time zone. I should be online again next Sunday. So thank you everybody so much for joining. With that, let me close the stream and say I hope to see you all again very, very soon.
Thanks for having us.
Bye-bye.